An Elementary Course in Synthetic Projective Geometry by Derek Norman Lehmer. Chapter 10, On the History of Synthetic Projective Geometry. Section 179, Descriptive Geometry and the Second Revival. The second revival of pure geometry was again to take place at a time of great intellectual activity. The period at the close of the 18th century and the beginning of the 19th century is adorned with a glorious list of mighty names, among which are Gauss, Lagrange, Legendre, Laplace, Monge, Carnot, Poncelet, Cauchy, Fourier, Steiner, von Staudt, Möbius, Abel, and many others. The Renaissance may be said to date from the invention by Monge of the theory of descriptive geometry. Descriptive geometry is concerned with the representation of figures in space of 3 dimensions by means of space of 2 dimensions. The method commonly used consists of projecting the space figure on 2 planes, a vertical and horizontal plane being most convenient. The projections being made almost simply for metrical purposes from infinity in direction perpendicular to the 2 planes of projection. These 2 planes are then made to coincide by revolving the horizontal into the vertical about their common line. Such is the method of descriptive geometry in which, in the hands of Monge, acquired wonderful generality and elegance. Problems concerning fortifications were worked out so quickly by this method that the commandant at the military school at Mézières, where Monge was draftsman and pupil, viewed the results with distrust. Monge afterward became professor of mathematics at Mézières and gathered around him a group of students destined to share in the advancement of pure geometry. Among these were Hachette, Briançon, Dupont, Chauselet, Poncelet, and others. Section 180, Duality, Homology, Continuity, Contingent Relations. Analytic geometry had left little to do in the way of discovery of new material, and the mathematical world was ready for the construction of the edifice. The activities of the group of men that followed Monge were directed toward this end, and we now begin to hear of the great unifying notions of duality, homology, continuity, contingent relations, and the like. The devotees of pure geometry were beginning to feel the need for a basis for their science, which should be at once as general and as rigorous as that of the analyst. Their dream was the building up of a system of geometry which should be independent of analysis. Monge, and after him Poncelet, spent much thought on the so-called principle of continuity, afterwards discussed by Chasles under the name of the principle of contingent relations. To get a clear idea of this principle, consider a theorem in geometry in the proof of which certain auxiliary elements are employed. These elements do not appear in the statement of the theorem, and the theorem might possibly be proved without them. In drawing the figure for the proof of the theorem, however, some of these elements may not appear, or, as the analyst would say, they become imaginary. No matter, says the principle of contingent relations, the theorem is true and the proof is valid whether the elements used in the proof are real or imaginary. Section 181. Poncelet and Cauchy. The efforts of Poncelet to compel the acceptance of his principle independent of analysis resulted in a bitter and perhaps fruitless controversy between him and the great analyst Cauchy. In his review of Poncelet's great work on the projective properties of figures, Cauchy says, in his preliminary discourse, the author insists once more on the necessity of admitting into geometry what he calls the principle of continuity. We have already discussed that principle, and we have found that the principle is, properly speaking, only a strong induction, which cannot be indiscriminately applied to all sorts of questions in geometry, nor even in analysis. The reasons which we have given as the basis for our opinion are not affected by the considerations which the author has developed in his Traité des propriétés des projectives des figures. Although this principle is constantly made use of at the present day in all sorts of investigations, careful geometricians are in agreement with Cauchy in this matter, and use it only as a convenient working tool for purposes of exploration. The one-to-one correspondence between geometric forms and algebraic analysis is subject to many important exceptions. The field of analysis is much more general than the field of geometry. And while there may be a clear notion in analysis to correspond to every notion in geometry, the opposite is not true. Thus, in analysis we can deal with 4 coordinates as well as with 3, but the existence of a space of 4 dimensions to correspond to it does not therefore follow. When the geometer speaks of the 2 real or imaginary intersections of a straight line with a conic, he is really speaking in the language of algebra. Apart from the algebra involved, it is the height of absurdity to try to distinguish between the 2 points in which a line fails to meet a conic. Section 182. The work of Poncelet. The Poncelet's right to the title, the father of modern geometry, does not stand or fall with the principle of contingent relations, in spite of the fact that he considered this principle the most important of all his discoveries. His reputation rests on more solid foundations. He was the first to study figures in homology, which is in effect the collineation described in section 175, where corresponding points lie on straight lines through a fixed point. He was the first to give, by means of the theory of poles and polars, a transformation by which an element is transformed into another of the different sort. Point-to-point transformations will sometimes generalize a theorem, but the transformation discovered by Poncelet may throw a theorem into one of an entirely different aspect. The principle of duality, first stated in definite form by Gourgaud, the editor of the mathematical journal in which Poncelet published his researches, was based by Poncelet on his theory of poles and polars. He also put into definite form the notion of the infinitely distant elements in space as all lying on a plane at infinity. Section 183. The debt which analytic geometry owes to synthetic geometry. The reaction of pure geometry on analytic geometry is clearly seen in the development of the notion of the class of a curve, which is the number of tangents that may be drawn from a point in a plane to a given curve lying in that plane. If a point moves along a conic, it is easy to show, and the student is recommended to furnish the proof, that the polar line with respect to a conic remains tangent to another conic. This may be expressed by the statement that the conic is of the second order and also of the second class. It might be thought that if a point moved along a cubic curve, its polar line with respect to a conic would remain tangent to another cubic curve. This is not the case, however, and the investigations of Poncelet and others to determine the class of a given curve were afterward completed by Plücker. The notion of geometrical transformation led also to the very important developments in the theory of invariance, which geometrically are the elements and the configurations which are not affected by the transformation. The anharmonic ratio of 4 points is such an invariant, since it remains unaltered under all projective transformations. Section 184. Steiner and his work. In the work of Poncelet and his contemporaries, Chasles, Briançon, Hachette, Dupin, Gourgaud, and others, the anharmonic ratio enjoyed a fundamental role. It was made also the basis of the great work of Steiner, who was the first to treat of the conic not as the projection of a circle, but as the locus of intersection of corresponding rays of 2 projective pencils. Steiner not only related to each other in one-to-one correspondence point rows and pencils and all the other fundamental forms, but he set into correspondence even curves and surfaces of higher degrees. This new and fertile conception gave him an easy and direct route into the most abstract and difficult regions of pure geometry. Much of his work was given without any indication of the method by which he had arrived at it, and many of his results have only recently been verified. Von Staudt and his works. To complete the theory of geometry as we have it today, it only remained to free it from its dependence on the symmetrical basis of the anharmonic ratio. This work was accomplished by von Staudt, who applied himself to the restatement of the theory of geometry in a form independent of analytic and metrical notions. The method which has been used in Chapter 2 to develop the notion of 4 harmonic points by means of the complete quadrilateral is due to von Staudt. His work is characterized by a most remarkable generality in that he is able to discuss real and imaginary forms with equal ease. Thus, he assumes a one-to-one correspondence between the points and lines of a plane and defines a conic as the locus of points which lie on their corresponding lines, and a pencil of rays of the second order as the system of lines which pass through their corresponding points. The point row and pencil of the second order may be real or imaginary, but his theorems still apply. An illustration of a correspondence of this sort, where the conic is imaginary, is given in section 15 of the first chapter. In defining conjugate imaginary points on a line, von Staudt makes use of an involution of points having no double points. His methods, while elegant and powerful, are hardly adapted to an elementary course, but Ray and others have done much towards simplifying his presentation. Section 186. Recent developments. It would be only confusing to the student to attempt to trace here the later developments of the science of projective geometry. It is concerned for the most part with curves and surfaces of a higher degree than the second. Purely synthetic methods have been used with marked success in the study of the straight line in space. The struggle between analysis and pure geometry has long since come to an end. Each has its distinct advantages, and the mathematician who cultivates one at the expense of the other will never attain the results that he would attain if both methods were equally ready to his hand. Pure geometry has, to its credit, some of the finest discoveries in mathematics, and need not apologize for having been born. The day of its usefulness has not passed with the invention of abridged notation and of short methods in analysis. While we may be certain that any geometrical problem may always be stated in analytic form, it does not follow that the statement will be simple or easily interpreted. For many mathematicians, the geometric intuitions are weak, and for such the method will have little attraction. On the other hand, there will always be those for whom the subject will have a peculiar glamour, who will follow with delight the curious and unexpected relations between the forms of space. There is a corresponding pleasure, doubtless, for the analyst in tracing the marvelous connections between the various fields in which he wanders, and it is as absurd to shut one's eyes to the beauties in one as it is to ignore those in the other. Let us cultivate geometry, then, says Darboux, without wishing in all points to equal it in its rival. Besides, if we were tempted to neglect it, it would not be long in finding, in the application of mathematics, as once it has already done, the means of renewing its life, and of developing itself anew. It is like the giant Antaeus, who renewed his strength by touching the earth. An elementary course in synthetic projective geometry. This book was written by Derek Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn and Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg. Read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.